Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera, good morning. This is lecture number 6 on orthosis, where we will cover how to determine the sample size of our experiment. So this is from the previous slides on the product development. It is very important for us to do testing, and when we do testing, we usually compare the efficacy of our design with existing system, so what we call intervention with the non-intervention. So we need to know whether the results are meaningful, whether it provides a significant improvement of the performance. So, and why we need to use statistics is because we want to produce the same data that anybody who look at it will draw the same conclusion using some standardized techniques, and also to be able to rationally handle biases and identify the effect is not due to random or chance. And if the effect is not meaningful, we can stop the development work, therefore saving ourselves a lot of trouble and money. And there are several steps that we have to follow, which we covered last time, and where we usually use hypothesis testing, where it is a statistical way of testing the results of experiment for meaningful results. And then we validate the validity of results are evaluated by calculating the probability of the results, and then whether the experiment is repeatable or not. So we cover null hypothesis. You need to figure out your null hypothesis, very important. Usually assume that it is what we don't want to happen, which is like the orthosis or the intervention does not make any changes or similar to the non-intervention. And then that is the null hypothesis, and then we do our test, a t-test to perform, and then when t is larger than the theoretical value that can be found in the table, we reject the null hypothesis and we accept the alternative of this. So we reject H0 and we accept H subscript A. So come to the idea of when we do experiment, we need to know the sample size. How big is our sample? So if it is too big, it might cost us a lot of money and time. If it is small enough, it's too small, it may not be able to handle or give us the kind of results that we want. So we come to what we call as power analysis. So sample size determination is the act of choosing the number of observations to include in a statistical sample in order to make inferences about a population from a sample. So power analysis is increasing the sample size. The hypothesis gains a greater ability to detect small effects. Okay, so the goal is to collect a large enough sample to have sufficient power to detect a meaningful effect. Okay, so what is the size of the sample, number of sample, which is large enough to have sufficient power to detect a meaningful effect? Okay, these are the words that we have to translate into mathematics later on. So, but not too large to be wasteful. So there is a technique for us to investigate. So because this is important in carrying out, before we can carry out the experiment, to estimate the cost of our project or how much money we need to invest in the test. So we have to do this sample size analysis. So power analysis, as it is known, combines statistical analysis, subject area knowledge, and your requirements to help you derive the optimal sample size for your study. So statistical power in a hypothesis test is the probability that the test will detect an effect that actually exists. So the level of probability could be 80% or more. Usually it's about 80% or 90% or 95%. So we want that probability to detect an effect, the effect that we want that actually exists in the population. So there are various types of outcome. So two types of outcome: dichotomous versus continuous outcome, and dichotomous versus continuous variables. So you might come across to these terms. So let's see the meaning of this term. Dichotomous or categorical, there are only two possible values, either male or female, dead or alive, or yes or no. For continuous, there are values between the ends. Okay, between black and white, there are gray scales. Between 0 and 1, there are 0.1, 0.2, and so on. So these are most of the samples, like the pH are continuous, the blood sugar level is continuous, blood pressure is continuous. Yeah, so these are continuous numbers. Two-sample t-test is used when the data of two samples are statistically independent. So remember, if there's two samples are statistically independent, we can call it two-sample t-test. Paired t-test is when data is in the form of matched pairs. However, if we have n matched pairs, the actual sample size is n pairs. Although we have the number of pairs is n, although we may have data from 2n different subjects. Yeah? So a pair consists of 2, so n pairs will have 2n of subjects. Kalau ada 4 pasang, maknanya ada 8 sampel. Matched samples, also called matched paired samples or dependent samples, are paired up so that the participants share every characteristics except for the one under investigation. Okay, so a participant is a member of the sample and can be a person, object, or thing. A common use for matched pair is to assign one individual to a treatment group and another to a control group. This process called matching is used in matched pairs design. The pairs don't have to be different people. They could be the same individuals but at different time. Okay, so that's dichotomous, dead or alive, yes or no, continuous, 0, 0.1, 0.12, 0.15 up to. So that's basically the idea of dichotomous and continuous. So factors involved in statistical significance. Okay, so look at the chart below and identify which study between A and B found a real treatment effect and which one did not. So within each study, the difference between the treatment group, say the left is a treatment group and the right is a control group. For study B, the left is the treatment group and the right is the control group. So within each study, the difference between the treatment group and the control group is the sample estimate of the effect size. So the estimated effects in both studies can represent either a real effect or it may be a random error. So let's see what is it. The difference between the treatment group and the control group is the sample estimate of the effect size. So we look at the difference here. So now it's called the effect size. So same here, effect size. So we can see that group A seems to have a larger effect size than group B, but there might be some problem with the statistics later on. So hypothesis effects tests incorporate these considerations to determine whether the results are statistically significant. So we have this word here, statistically significant. So effect size. What is the effect size? It is that the larger effect size, the less likely it is to be random error. It is clear that from the previous slide that study A exhibits a more substantial effect in the sample, but that's not sufficient. That is insufficient by itself. Just looking at the mean or the difference between the mean is not sufficient because of the sample size effect. So we've got another problem with sample size effect. Okay. So larger sample size allow hypothesis tests to detect small effects. So if you're looking for small effects, you really need to have larger sample size. So if body sample size is large enough, its more modest effect can be statistically significant. So even though the difference between the left and right is small, but if the sample size is large enough, it can be statistically significant. The third issue is the variability. Okay, so when your sample data have greater variability, random sampling error is more likely to produce considerable differences, okay, between the experimental groups, even when there is no real effect. If the sample data in study A have sufficient variability, random error might be responsible for the large difference. So this is the third issue. So the effect size, sample size, and variability. So how do you measure variability? Let's digress a little bit. How do you measure variability? So hypothesis testing takes all this information. Hypothesis testing takes all this information and uses it to calculate the p-value, which we use to determine the statistical significance. Statistical significance of any effect depends collectively on the effect size, sample size, and variability. So remember this: effect size, sample size, and the variability in the sample data. So you need these three data to determine the good sample size. You cannot determine a good sample size in a vacuum because the three factors are intertwined. They are all connected together. So statistical significance depends on your effect size, sample size, and variability. So these all three will then influence the statistical significance. Let me check this. So it will influence the statistical significance. So this one will be influenced by this, and influenced by these three things. So we now come to the statistical power of a hypothesis test. Statistical power is the probability that a hypothesis test correctly infers that a sample effect exists in the population. Okay, we want to prove that that effect exists in the population. So the test correctly rejects a false null hypothesis. Consequently, power is inversely related to a type 2 error. So do this study on yourself. Type 1 error is related to alpha, type 2 error is related to beta, and statistical power is known as 1 minus beta. While alpha relates to the p-value, beta relates to the power. Typically beta is 0.2, or you might go to 0.1 or 0.05. What it says that if our study has 80% power, i.e. power equals to 0.8, it has an 80% chance of detecting an effect that exists. And the power of the test depends on other three factors as we have covered before. So why do we need to calculate the power? Because when an effect actually exists in the population, the study might not detect it because of the statistical characteristics of a sample. So samples contain sample error, where a random sample misrepresents the population. There is this probability that you will miss out the effect that we are looking at. Okay, so we need to know the power, statistical power of our sample. So how do we do that? So goals of a power and sample size analysis is that powerful study requires large sample and can detect an effect that is small, but is it useful? Underpowered study that has a low probability of detecting an important effect. If you do not have enough population, enough sample, you might miss the effect. And what is a good effect? Well, it depends on the subject matter expert. Okay, so 4 parameters are required in Bowers analysis: sample size, differences. So here the differences refers to the smallest differences that matter. For example, we're looking at the difference of 5 megapascal in the tensile strength, or which below that it does not matter to us, or it doesn't make a difference. Number 3 is power value. So, for example, a power of 0.9, so that 2 sample t-test has a 90% chance of detecting a difference of 5. 5 refers to the 5 megapascal here. Number 4 is a standard deviation, a measure of data variability. This can be based on the pilot study done earlier. So usually we have a pilot study to determine the standard deviation. From that we can use the standard deviation. Here in this case the standard deviation is 4. So that's assumed that's 4. So for this we are looking at we need the standard deviation to be able to do our prediction. So in designing studies, most people consider power of 80% or 90%. Just as we generally use 95% as the confidence level for confidence interval estimates, the inputs for the sample size formula include the desired power, the level of significance, and the effect size. The effect size is selected to represent a clinically meaningful or practically important difference in the parameter of interest, as we will show later on. So the formulas we present below produce the minimum sample size to ensure that the test of hypothesis will have a specified probability of rejecting the null hypothesis when it is false. That is the specified power. So in planning the studies, investigators again must account for attrition or loss to follow up. Sometimes when we carry out the study, for example, there are 30 people, 2 of them did not show up, or 2 of them died, or for that reason. So we need to also make the number of sample a bit larger in order for us to not go below the minimum value of sample in order to achieve our p-value of 0.05 and beta of 0.2. So the formula shown below produces a number of participants needed with complete data. Okay, so this is 3 situations. There are 5 situations, but I'm only looking at continuous outcome. So this is the case for continuous outcome. Remember we talked about the differences between dichotomous and continuous. Yeah, this is not do or die, yes or no, but this is somewhere between 1, 1.2, 1.5 and so on. So there are cases for 1 sample. There are cases for 2 independent samples. And there are cases of 2 matched samples. Okay. So for each sample, the confidence interval is a bit different. You can see here, for H0, mu equals to mu naught for 1 sample. The population sample is equivalent to the sample mean. The 2 independent sample is that we assume that for the null hypothesis, H0 equals to the means are similar. Yeah. The means are similar here. So if you don't see them, let me write it down for you. So here is that the H0, the null hypothesis is that the mean are the same. Okay. And then for 1 sample, we said that assuming that the sample from that one, the mean is equivalent to the population sample. The sample mean is equivalent to the population mean. For 2 mesh sample, we have to decide the confidence interval for mu d, but here is the difference is that our H0, we say that the difference is none. So between that sample, mu d equals to 0. So this is the confidence interval to be calculated. This is for one sample, this is for two samples, and this is for matched samples. So not much different, except the word 2 here. And then sample size have got different sets of formula, but the effect size is just a bit different. This is not equal, but minus. This is minus. This is minus. Yeah, and then Z values and so on. So in this lecture, we will only consider 3 cases, i.e. for one sample, 2 independent samples, only 3 cases. One sample, 2 independent samples, and 2 matched samples. And we'll cover the example of each. So type 1 is the one sample continuous outcome. In studies where the plan is to perform a test of hypothesis, comparing the mean of a continuous outcome variable in a single population to a known mean, the hypotheses of interest are here. So we assume that H0 mu equals to mu naught, and H1 mu is the alternative is that mu is not the same. So mu naught is the known mean, okay, and then the formula for determining sample size to ensure that the test has a specified power is given below. Yeah, so n equals to z subscript 1 minus alpha over 2 plus z1 minus beta divided by effect size and square of that. So where alpha is the selected level of significance, usually 0.05, and z for that is the value from standard normal distribution holding minus alpha below it. For example, if alpha equals to 0.05, then 1 minus alpha over 2 is 0.975, and you can find the z value is 1.96. So for z, 1 minus alpha over 2 in this case is 1.960 for the case of alpha equals to 0.05, and then yeah, so then 1 minus alpha over 2 is 0.975. You can get z values. 1 minus beta is the selected power, and z subscript 1 minus beta is the value from the standard normal distribution holding 1 minus beta below it. The words are almost the same with alpha. Sample size estimate for hypothesis testing are often based on achieving 80% or 90% power. So in this case, we assume 80% power. So z for 1 minus beta, beta equals to 0.2. So z subscript 0.8. The answer for that is 0.84. Okay, and for 90% power, z is 1.282. So the effect size is the difference of the mean, mu1 minus mu naught. So mu naught is the mean under H0, mu1 is the mean under H1, and sigma is the standard deviation of the outcome of interest. So the numerator is the top part. The effect size is the absolute value of the difference in means. Represents clinically meaningful or practically important difference in mean. For example, we can see that a drop of temperature by 2 Celsius is the meaningful effect. So mu1 minus mu naught should be larger than 2 Celsius. It is difficult to estimate the standard deviation. Remember, we need a standard deviation to find the effect size. Use a value from a previous study. So you need to find papers that carry out the same thing, or a study performed in a different but comparable population. This is your biggest task, to find other papers that could give you some idea where your work is. Regardless of how the estimate of the variability of the outcome is derived, it should always be conservative, i.e. it should be as large as reasonable, and so that the resultant sample size will not be too small. So you need to use a lot of techniques like randomize, and then you have to do multi-site in order to find a good population. So example 1. In this example, a cross-sectional study is planned to assess the mean fasting blood glucose level in people who drink at least 2 cups of coffee per day. The mean fasting blood glucose in people free of diabetes is reported as 95 milligram per deciliter, and the standard deviation is 9.8 milligram per deciliter. If the mean blood glucose level in people who drink at least 2 cups of coffee per day is 100 milligram per deciliter, okay, this would be important clinically. So the difference of 195 is 5. So that is the difference of the mean. So how many patients should be enrolled in the study to ensure that the power of the test is 80% to detect this difference? A two-sided test will be used with 5% level significance. So we calculate the effect size ES as the difference of mean divided by the standard deviation. So where is the standard deviation? It's here. The standard deviation is here. So let me highlight that in green. So that's your standard deviation, 9.8 milligram per deciliter. So 100 minus 95 divided by 9.8, the effect size is 0.51. The other part is to apply the formula n equal to z 1 minus alpha over 2. So we look at the books. So z minus 0.05 divided by 2 is 1.96, the value of z. And z for 1 minus beta is 0.84 divided by the effect size. So divided by 0.51, and we can find that the number of participants of 31. So 30.1, so we need to be larger than this. So a sample size of 31 will ensure that the two-sided test with alpha of 0.05 has an 80% power to detect. This is what we call the significant difference or meaningful difference, 5 milligram per deciliter in mean fasting blood glucose level. So next one. So to account for non-compliance, we put some extra samples inside, so that here we set number to enroll, percentage of following and protocol, and desired sample size. So we think that 10% might not be there, so we review the number. 31 divided by 0.9, we have 35. So 35 is the participants that we want, assuming that 3 of them will not finish the study. Okay, so there is a buffer there. Type 2, 2 independent samples, continuous outcome. So an investigator is planning a clinical trial to evaluate the efficacy of a new drug designed to reduce systolic blood pressure. The plan is to enroll participants and to randomly assign them to receive either the new drug or a placebo. Okay. So the systolic blood pressure will be measured in each participant after 12 weeks. So this is the post-treatment. Based on prior experience, similar trial, investigator expect 10% of all participants will be lost to follow up or will drop out of the study. So if the new drug show a 5-unit reduction in mean systolic blood pressure, okay, this would represent a clinically meaningful reduction. How many patients should be enrolled in the trial to ensure that the power of the test is 80% to detect this difference? Then a two-sided test will be used, and 5% level alpha is 0.005 or 5% level of significance. So you calculate the effect size. Here ES equals to the difference of the mean mu1 minus mu2 divided by standard deviation. So we know that the significant difference is 5 and the standard deviation is given by 19, so you get the effect size of 0.26. We substitute the effect size and the appropriate Z values for the selected alpha and power to compute the sample size. So we find Z at 1 minus 0.025, and for beta equals to 1 minus beta equals 0.8. When we find this answer 1.96 plus 0.84, this has, you got to refer to the tables, yeah, and divided by the effect size of 0.26, we have the number of participants for this study, 232. So we hypothesize a test 10% attrition rate, so only 0.9 will stay on, so that 232 divided by 0.9, and we have 258. Okay, so we need to have 258 participants to be randomly assigned to receive either the new drug or placebo. So this is for outcome of two samples. Type 3 is the matched sample and continuous outcome. So in studies where the plan is to perform a test of hypothesis on the mean difference in a continuous outcome variable based on matched data, the hypothesis of interest is shown like this. So H naught equals to mu D equals to 0. So the difference is not, it's the same. 0 means there is no difference. Versus the alternative is H1 mu D is not 0. So mu is the mean difference in the population. Mu D is the mean difference in the population. And then we need to do the sample size to ensure that the test has specified power. They almost have the same kind of formula. Alpha level of significance, Z minus 1 alpha, as we have done before, using standard normal distribution, holding 1 minus alpha below it. 1 minus beta is power, and Z subscript 1 minus beta, we can obtain that from the chart, standard normal distribution, holding 1 minus beta below it. So here is a case, exercise 3, to evaluate the efficacy of an acupuncture treatment for reducing pain in patients with chronic migraine headache, where each of them will be asked to rate the severity of the pain 1 to 100 that they experience with their next migraine before and after treatment is administered. So the difference in pain will be computed for each patient. A two-sided test of hypothesis will be conducted at alpha equals to 0.05 two-sided test and power of 80% to detect a difference of 10 units on the pain scale. How many patients are needed? Assume that the standard deviation, this is assume again, yeah. Assume that the standard deviation in the difference score is approximately 20 units. So whatever you do, first compute the effect size. Here mu D divided by sigma D. So standard deviation is known as 20, and the difference of mean is about 10 of meaningful difference is 0. The effect size is half. So then we calculate the sample size. So Z alpha and Z beta divided by effect size to the power of 2. And then this is 1.96 plus 0.84, and then 0.50 equals to 31.4. You can now see the trend already. You can see the trend already. You can see that this Z1 minus alpha and Z minus beta, this is almost like alpha, almost constant at 0.05. 1 minus beta is almost like constant at 80% or 90%. So then the value of alpha 1.96 will always be there, and value of Z beta 0.84 will always be there. So you just need to determine the effect size in order for you to determine N. So here we got 31.4. So here we have 31.4 as the answer. So then we said it's about 32. So then we said 31.4 is about 32 patients. So that we now know that we need this 32 patient with migraine to ensure that the two-sided test with significance of 0.05 and 80% power to detect a mean difference of 10 points in pain before and after treatment, assuming that all 32 patients complete the treatment. So now I've shown you 3 examples of type 1, type 2, type 3 on how you could determine the effect size. You know what the effect size is, and you can now calculate the sample size of the population for you to carry out the clinical trial or to do the experiment. So here's the link. You can go and study them in more details. I hope you have benefited from this lecture, and please carry on studying on yourself. But the materials presented here provide you enough background for you to move on to the next level. So thank you very much. We'll see you in the next lecture. Oh, before that, this is final table. This is to show you the effect of confidence interval reduction on the true difference of mean. Yeah, so let's spend a bit more time here. Effect of confidence interval reduction to demonstrate a true difference in mean. So what happened? So the first study here shows the main value. So group 1 is compared with group So this example shows the initial comparison between group 1 and 3. So group 1, n equals to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9. So group 1 has 9 equal 9, and group 3 has n equals 9. So the other group, in the second study, what happened is that if I enlarge group 1, the sample to same, but now the sample becomes double, n equals to 18. And I also enlarge group 3 to grow in the sample size with the same kind of data. The mean doesn't change, yeah, but now n equals to 18, yeah. So now first you will do the comparison group 1 versus group 3, and then with enlarged size of participants, so group 2 versus group 4. So here is the plot of the confidence interval of 95% confidence interval. So we have a 95% confidence interval. Sorry. So we've got a 95% confidence. So here is the 95% confidence interval. Okay, and then the mean value. So this is the mean value. Let's put it in blue. So that's the mean value for group number 1. And here in purple is group 2. So when you enlarge the size, the mean value stays the same. Okay? But the confidence interval reduces. So the size, the confidence interval reduces. So you can see that this one is reducing. Yeah, so it gets smaller, and similarly for group 2, it gets smaller, but the mean value doesn't change. So now, should no statistical difference as the confidence interval overlap. So if the cases here where the confidence interval overlap shows that it's not enough statistical difference, okay, but as you enlarge the population size, you can see that there is a gap between the confidence interval. So now you can see that the confidence interval no longer overlap. Yeah, so we can see that the confidence no longer overlap, indicating that the difference in means is unlikely to occur by chance. So it's important for you to see from this simple experimental work, statistical work, yeah, group 1, 9, when we increase the number of samples, double the number of samples, we do not change the mean value, but we change the confidence interval. So this is also one way to show that the significant difference is when the confidence interval does not overlap. So that's a good, I guess it's a good way of looking and understanding it. This is more indicative for and easier for us to understand when we can graphically notice the changes when we increase the sample size. The mean stays the same, the confidence interval shrink, and what we want to see is the separation between the confidence interval here that gives us the indication that the difference in means here is not to have occurred by chance. Though the means are different, the location of the means doesn't change, but then there is no overlapping of the confidence interval. So guys, that's basically the true end of this lecture, and I hope and wish you all the best. Stay safe and see you in the next lecture. Assalamualaikum warahmatullahi wabarakatuh.